That's good.
I have no idea where it's recording, but hopefully it's actually being recording.
We'll be able to find it somewhere.
Yeah. Yes. For everyone that is just getting here. And we're almost ready to get started. Does anyone have any logistical questions about anything before we begin? This should last 1.5 hours, I guess minus 10 minutes.
Okay, it looks like 12:40, so I'll just get started. Hello everyone. Welcome to the topical review session. Today's review session is going to be on iterators and generators. It's going to be by me and Dalton, who's in the chat right now. Yeah, I'll be starting on iterators, and then I'll go over some mini lecture about iterators, and then we'll switch to Dalton, who's going to be talking about generators. And then we'll have coding questions for you to work on. The slides is in the Zoom chat. So if you want to look at the slides and follow along, that's fine too. Yeah. If Dalton will be answering questions in chat. So if you have any questions, you can just ask in chat, or you can just say it out loud and I'll answer them. All right. Okay, cool. So first thing to remember is something about iterables. So essentially anything that has some element that can be looped over is called an iterable in Python. And essentially for iterables, you can call iter, the method iter, which is a built-in method on it, to get an iterator. And this iterator will be important later on. Some examples of iterables are strings, in which case you iterate over the characters in the string. You have lists, in which case you iterate over the the elements inside the list. Or if you just iterate over dictionaries, you'll iterate over the keys in the dictionary. And those are iterables. Also, something to take note is that all iterators are also iterables. So you can call iter on an iterator to get the iterator. All right. Okay. So, iterator. Oh, yes, it's on the next slide. Iterator is an object which keeps track of locations in an iterable. So it's like, you can think of it as like a bookmark, or it's like kind of like a pointer. You have some elements, and then you just have a point to a specific element. And you have as many of these bookmarks as possible, but each one can have a different location. And how to use iterators is that you call next on it, which will get the current element. It will return the current element, and then move the bookmark to the next element. And because iterators are also iterables, you can call iter on them. It will just return a stop. And I think, well, also when you get to the last element, it will raise the stop iteration error for you to know that this iterator has reached the end. All right. Next. So you can't call next on it until it runs out of elements. So if it reaches the end, it will reach a stop iteration exception. I don't think we really covered exceptions in this semester. So yeah, just think of it as some error happens and you will be able to find it. So the for loop in Python automatically finds it. This question cannot be this Python. Sorry, I can't hear you properly. Wait, Dalton.
I'm not sure they're asking a question. Are you asking a question, or is there just background noise? Felix.
So remember to use
okay.
I don't know. If you have questions, like I couldn't really hear that, but if you had a question, please ask in chat and Dalton will answer it. Yeah. All right.
But now we have to leverage
Oh, so you you can mute participants.
Yeah, I think they are watching a lecture or something. There we go. There you go. All right. Okay. So here's the diagram. There are iterables and here's iterators. So next is anything that's iterable. I mean, in iterator you can call it. I actually don't know what this diagram is for. Let's just pretend we didn't see this. Okay. Some extra things to take note is calling a list on any iterable will first call iter on it, and then call next repeatedly until stop iteration, and then collects the returned elements into a list. Right. Also, calling next list on iterator will do the same thing. Yeah. Wait, calling iter on iterator does not refresh. Oh yeah, that's right. If you call iterator on an iter on the iterator, it does not refresh the bookmark. All right. So we'll actually start where it left off. It will permanently move the bookmark to the end. Reason is because calling iter on an iterator just returns itself. Yeah. So one thing to take note is, yeah, sometimes if you write range, like things like range, it will actually be a range object. So to actually get the elements to get like the list that's 0, 1, 2, 3, 4, etc., you have to do list on range, things like that. All right. Okay. So here's a small example. You have list 1, 2, 3, 4, 5, 6, 7. The first iterator, call iterator, it will be right here. And then list 2, it will be right here. And iterator 3, on iterator 2, it will actually be the same iterator. So just be I2. So it'll be a pointer to the same iterator object. Calling next on I1 will advance this and return 1. Okay. A list 0, it doesn't change the list, so it's still 1. I mean, sorry. Calling iterator doesn't change the list. So list 0 will still be the first element, and then change that to 33. Next on I2, we return 33 in this case because it's changed. And then go to the second one, I1, then B3, and then I1 again. Okay, it will be 3 that time. I2 will be 2, and then move to the next one. I3 will actually be I2 again because it's the same thing. So that will be 3 and move I2 to the next one. Yeah. Wait, any questions on like this part? I'm going to pretend there's no questions on this part. So I'll move on. So actually on this final exam, there won't be actually Python display questions because it's open interpreter. So it will be kind of pointless to have, Python display questions. Yeah, but so here's just some interesting things to look at. If you do list is that, iter on list is 1, next on 1 is 1. And then this one should also be 1 because it's a different iterator. Wait, so there are environment diagrams for no time. Yeah, so there will be environment diagrams, but there will be like a weird type of environment diagram in which you're given the diagram and you're supposed to fill out the code part for the environment diagram. So it's kind of like a reverse environment diagram. And I think we'll give you like, it's not just like you can fill out whatever, we'll give you like a multiple choice of things to fill out in each blank. So it's not just like completely random. Yeah. Okay. Here's another one. List 1, 2, 3, 4, 5. It's not as important just because there's no Python display. So we have this. Calling next on it twice. We'll iterate it, advance it twice. So it'll be on 3. And then calling next on I. Oh, calling next on it and printing it will be 3, 4, 5. And then just error because you can't call it. Yeah. All right. Here's another one. This will print out 3, 4, 5 because this has already advanced it 2 times. And then this one will print out nothing because this is already at the end since we're using the same iterator. All right. Okay. Okay, so we have next part, generators. It's very closely linked to iterators. So Dalton, do you want to take control of the screen?
Yeah. So I was gonna kind of scour for the answer to this question, but Sage asked, will we be able to use the tutor function from 61A website during the final? And my knee-jerk reaction is yes.
Yes, I
You're
think
allowed to do that before. But I don't know 100% because I don't know if John has said anything about that. So I don't want to make a official statement. If you know, then you can make an official statement.
It's open. It's open.
Yeah.
It's open interpreter and open 61a.org.
Yeah, that's what I would think. So
it should be.
Okay. So yes. And then there's another question, but I'll move on to generators. So let's see if I can control this. I'll click on it.
I have a question here.
Yes.
Yep.
And you mean the first for loop will print out 3, 4, 5, but the next for loop will be the iterator will be the end, so we will not print anything?
That's right. Because remember, for loops they call like iter on whatever you pass in, and since we're iterating over an iterator, it will call iter on the iterator, which returns itself. So if the first for loop got to the end, the second for loop is already at the end, so it won't actually do anything.
So we will print nothing or none or.
Yeah, it just doesn't do anything. The second for loop doesn't do anything.
Okay, thank you.
All right.
Okay, so I think the demo test should be close to the format of the exam. Of course, it's always subject to change. So no idea. I don't know if there's an answer key. I think it's just so you know how long the test is, what kind of questions are on it. Not that is a practice exam. Okay, Charles, you can answer the rest of the text questions. I'm going to move on to generators. So generators, yeah, we're going to talk a bit about generators because there's a lot to break down here. We'll kind of start with the idea of a generator function, which is that you are kind of just typing out a regular Python function, but in the most common of cases, you're just replacing your return statements with yield statements. So you just replace your returns with yields, and now you have this completely different Python thing, which acts differently than a normal function. And the number one, instant difference between generator functions and regular Python functions is that generator functions, when you call them, it does not evaluate the body of the function. So what does it do? Well, when you call a generator function, all it does is evaluate to a new generator object, which is kind of like an iterator over this function. So when you call a generator function, the body is not evaluated. Instead, you just kind of place this bookmark at the very beginning of the function, and you say, this is now my generator object. And if I want to start, calling next on it, you can start going through the function, but nothing happens yet. Control. Okay. Did I skip something? No. Okay, so here's already a little what would Python display. So we have defining a generator, which has 2 lines. So if we said, assign x to the return value of generator called on 5, what happens? Think about it for a second. And error. I see error. Let's see. So the correct answer is not an error yet, because the body of a, no, it's all right. That's why we're here. So the body of a generator function is not evaluated when the generator function is called. So unlike a regular function, right, calling the generator doesn't actually run any of the lines inside the function. It's just going to kind of place this bookmark at the beginning and wait. So x is going to be the generator object. now if we call next on X, what happens? Take a minute. If you want to, you can write it out. Ooh, I see error. All right, cool. So that's totally right. What happens here, like, keeps not controlling the screen correctly. Oh, yeah, so next we get a 0 division error. So what happened? Well, when we called next, now we have this bookmark. The arrow is kind of our bookmark into the function. And we ran the first line of the function because we want to get a value, we want to get to a yield, but it errors and the program stops. So next, so what exactly happens with these yields? Generators are running, when you call next, it's going to start running the lines of the generator, and it's going to keep running them until it hits a yield statement. So when it hits the yield statement, it evaluates the yield statement, then it stops, and whatever the value was of that statement, that will be the value that is returned up to the next call. And the function is then paused until the next time you call next. And the next time, it's going to resume from the location where you left off. So that's why it's kind of like the bookmark example, or the idea of thinking of it like a bookmark is really applicable still, because your bookmark is saved in the function where you are. And kind of just like iterators in like a list or something, you can have many different bookmarks in the same function, in the same, so you have many different generator objects pointing to different places in your generator function. And when you start resuming again with the next call, it will start with the line after the yield that you just had, or not the line below, but whatever line would have ran if you were running it like a normal function. So yeah, so just one note about generators is that they're very useful for infinite sequences. So this is an example on the right of an infinite generator, where we have the generate naturals, which we have this while true, which will infinitely yield integers starting at 1. We can call it, it evaluates to the generator object, and then we can repeatedly call next on it forever. This is similar to kind of scheme streams. So we often see while true in generator statements, where we don't see that sometimes as much in regular Python functions. So yield and yield from. So we use yield when we want our generator to output like one specific value. So yield, if we want to yield 1 at some point, we yield 1, or we can yield X or anything like that. It kind of just works like return. Yield from is this special thing that we kind of add on. And yield from is just syntactic sugar in Python. Syntactic sugar means you never would actually need to use it, but sometimes it looks pretty. So we can see on the right-hand side, yield from anything is always exactly equal to, for each element in that thing, yield that thing. So those are the same, and anytime you wanted to yield from, you could just write the top thing. But yield from looks nice. So understanding for loops, we can understand what yield from does. It just goes for each element in that list, it yields it. And because we're yielding each time, it's going to pause after each time we extract something from our iterable. So if our iterable is infinite, this won't cause a problem because we're going to pause after each thing we're yielding. So we're only going to get the next element when we call next. And that's what allows us to do these infinite sequences without Python breaking. Usually Python breaks when we try to do like an infinite for loop or infinite while loop. But the generator idea is that it's going to pause after each time. So we're only going to get the next elements one at a time. So while true, common for infinite sequences, for loops, common for finite sequences, and you can also use recursion. Ooh, yay. I'm sure we're all very excited about using recursion and generators together. but it's not too bad, especially if you use the recursive leap of faith on a generator object. So moving on. Generators yield versus yield from. Yeah, so this is kind of the number one trippy thing for generators. So this is just a common mistake, which is that when you want to craft generators using recursion, oftentimes you want to be using yield from instead of yield. So when we yield, let's say the left example, right? We're yielding this recursive call. And we know that this is a generator object because we're using yields. So when we call a generator function, it returns a generator object. Therefore, if we yield just this thing on the left, yield mults of 3 called on something, we're going to be yielding a generator object, which is completely not the right type because we want to be yielding numbers, not generator objects. So that can be fixed on the right-hand side, where instead of using yield, we use yield from this recursive call. And we know that a generator is an iterable. So if we yield from this iterable, we're going to be plucking out each value. And because it's recursion, we can use the recursive leap of faith to just say, I believe via the leap of faith that this will, in fact, yield every single multiple of 3 from I plus 1 onwards. So we can just trust that this yield from will, in fact, grab every single one at a time forever and yield them continuously. And this is an infinite sequence, but again, the infinite sequence is fine because we're going to pause after each one. Only when we call next is it going to move on. So, and this is something that doesn't come up too often, but it has come up in the past. So just want to touch on it. You can have a return statement in a generator. A generator becomes a generator when you include at least one yield statement. So, but you can have a return as well in the generator. And a return basically, we can think, well, if we don't include a return, maybe eventually it runs off the very end of the function, just like a normal function. And we know that in normal functions, there is an implicit return none at the end of every function. Because if you hit the bottom of the function, you know that the return value is none. You can kind of just pretend that there's a return none at the bottom of every function anyway, and that always exists. So we can use a return statement in a generator to end stuff early and to raise that stop iteration exception. So if you encounter a return statement inside a generator, this stop iteration exception, which stops the generator, is immediately raised, and no more elements are yielded, including the value of the return statement. So I just want to be clear, like if you find that maybe you wanted to write a return statement in a generator, it only really makes sense to return nothing, because the return statement functions as just an end to the generator. You're not going to yield anything else. If you wanted to have one last yield, you could put a yield statement above it to say yield 3, and then you can return and end it. But return, just stops the generator, raises stop iteration, generator is dead, and you'll move on with your life. So that can happen sometimes. For example, this random generator function on the right, you can see the purpose of that is just, it will kind of yield still going, and then there's a 10% chance each time that the generator will just randomly die, and then it won't have any more elements. So that's kind of like a fun little generator, and it uses a return statement to end the while loop early. Otherwise, it would just keep going forever. So next, let's see. Okay, so we're gonna move on to the practice portion. So the rest of this will be practice time. We're gonna have some problems, and then the idea is that hopefully you do not just wait patiently for the solution and then look at the solution, or look early at the solution because you have the slides. It's very, very helpful if you try it yourself. Like grab a piece of paper. You can take a minute to grab a piece of paper if you want, or type up. You can type up a solution that you maybe are thinking about, because it really, really helps if you try to do these problems yourself. So we will give you time to do this. So after we introduce each problem, definitely I highly recommend trying these problems and then seeing where you get, and then we will talk about the solution afterwards. And if you want to check your work early, you can look at the slides that we've linked, and they're going to have the solutions just like right on the slide deck. So I believe after Charles is done answering this text question, then he will kind of start us off with this first problem.
Yes. Hi, welcome back. Yes, so we recommend getting a piece of paper to write some stuff down, but let me explain the question. So this generator function called unique, it takes in an iterable argument. So when I say it's iterable argument, it means that the argument is an actual, is an iterable, any iterables, not just lists. And then it returns an iterator over all the unique elements. So it says it returns an iterator over all the unique elements. What it means is just, it's a generator function. So it yields all the unique elements of its inputs in the order that they first appear. So, also it says implement unique without using a for loop statement. So, and also it has some restrictions. You may not use any define, for, or class statements or lambda expressions. Yeah. So as an example, if you call unique on iterable, it will be a generator. Remember, this is a generator. It will yield 1, 3, 2, and then the next time you call next, and then when you call next on it, it's going to see 2, and it's going to say, oh, I did it again. Okay, I'm going to go to the next one. So it's going to be 5, and then 3 is looked at already, so it's going to skip and go to 4, and then it's going to skip this one, and then it's going to stop. So yeah. So yeah, how long do you want to spend on this question? Yeah, let's just say around, let's just see 5 minutes, see what you can get up to in 5 minutes. And if everyone's still working at 5 minutes, then we can extend the time further. All right. Okay.
Sounds good to me.
In the meantime, if you have any questions, you can just say it out loud or type it in chat and we'll answer them.
Great. To answer those questions out loud, this question does not have skeleton code because that's not how it was written. There will be questions later in this whole thing that will have skeleton code, but yeah. So this one does not have a skeleton, but if you want codes with skeleton, hang tight. But solve this one too. You shouldn't always need a skeleton. Charles, are you answering Kai's question?
Oh, I'm answering a private question.
Okay.
Yeah. Yes. Yeah.
I'll just answer Kai's text so that everyone can see it.
All right, how's everyone going? Like you can go to the participants part and click on yes if you are finished and then no if you're not finished. Or
Like
or actually think about it this way. Instead of doing that, click on yes if you want a hint and no if you don't want a hint. Does people want a hint for this question?
All right. Click on participants at the bottom.
I'm seeing a lot of yeses. And some no's. Okay.
Oh wait, this is an interesting question. Charles, do you know if an exhausted iterator is falsy?
I do not think so.
You think it's truthy? Okay, let me check that.
I don't think iterators have a special like a Boolean method.
All objects have a.
Like I don't think they have a specially defined one.
Oh, I see. Let me try it.
That's an interesting question actually.
Oh yeah, an exhausted iterator is truthy. So let's see.
Yeah.
So how can you check an iterable empty after you iterate check was equal to null? No, so you can't check if it's iterable. Let's see. Let me try to type out an answer to Anthony's question.
Okay. Well, I'm going to do just a quick hint. So for this question, since we're looking for unique elements, right, then we need to have some way of keeping track of the elements we have seen. And then therefore, each time when we go through the elements, we can check whether we have seen it or not. So think about how we can do something like that. Also, if you're having trouble of like determining when the thing has ended, well, the thing is, when you call next on an iterator, if the element doesn't exist, then next will raise a stop iteration error, which means that the function itself is not going to catch that, which means that the iterator function will also raise a stop iteration error, which means that the generator has just finished because it has reached the stop iteration. So basically the idea is you don't actually have to check whether the iterator has finished or not, because if you're using a generate object, then it will do it automatically. So that may help with your stopping condition or lack thereof. Also, I think one thing is also taking note is you can't you can't necessarily index into an iterable. An iterable is just defined as something that you can call iter on, not like you can't not necessarily index into it. For example, lists are iterables and you can index into them, but iterators are also iterables, but you cannot index into an iterator. You can only call next on. So, yeah. Yeah.
I think we might be ready to go.
Yeah. Does everyone okay with us going over the answer right now, or do you still want more time? There's no real good way of doing this. Is there? Is there? I don't really want to do a poll. Can I do a poll? Who wants to go over the answer right now? Just click on yes if you want to. You don't have to. It's not required. You don't have to. Click on yes. Okay. Well, most people it seems like yes. If you don't want to go through the answer, what you can do is you can I guess I don't know, you can mute me and then just don't look at the screen, I guess. But yeah. Yeah, let's go with the answer. So as we were saying before, what you need to do is, or actually, does someone want to give the answer that they have? And does anyone want to volunteer their answer? You can, I guess, type in chat or like voice, or like voice explain it. Okay. So someone saying list equals.
We have the first line.
We have the first line. Okay, we have a very good first line. So we have some kind of list, which keeps track of what we have seen. So that's good. We have the first line. Okay, and then we create an iterator on the iterable. So that's very important. Instead of using indices into our iterable, we use iterator on it because, as I was saying before, not all iterables can be indexed into. Okay, well, you see, yes, we have a while loop. That is good. But the problem again is len does not work on iterators. Iterators only have next and iter actually. You only call iter on the iterator because it's an iterable, and you can't call next on it. Yes. So last has suggested while true, and yes, correct. That does work. If it's while true, then you don't have to index into anything because it will just keep going until a stop iteration is hit. That's correct. And if there's no more, I'll just show the answer. Let's while true check. So what does while true check? While true is just an infinite loop. It doesn't check anything. It checks whether true is true and true is true. So yeah, in Python, if you want to do an infinite loop, just do while true, and that's an infinite loop. what is iteration? What is iter? Iter calls, you might have missed the beginning of the mini lecture, but iter is, yeah, iter,
I can answer what is iter question on text.
Yeah.
If you just want to keep going over the answer.
Yeah. Okay, so I'm going to show the answer because we are very close to the right answer. So we have observe, which is a list that keeps track of observed. And then we have I is equal to iterable. So this I is an iterator. So that means iterable could be an infinite loop. An infinite iterable that also works. Now, while true, so we're just going to do the following things as many times as possible. So like forever, basically. Then we have to get the element by doing next on I. So we see someone saying yield x. You're very close. But the thing is, x doesn't actually exist yet. So we have to actually we have to find what x is. So we have to do something like x or element is equal to next on the iterator. And then we check if element, whether it's in observed or not. If it's not in observed, right, that means we haven't seen it before. We want to add it to the list of elements we have seen and then yield it. And that is, yeah, this whole thing. So how does the while loop stop if the condition is always true? That's a good question. So it stops because of this line. Element is equal to next of I. So the reason is, as we were saying before, next, what it does is it takes an element, it returns the current element and goes to the next one. And if you are on if you're at the end, so if you've gone through all the elements, calling next on the iterator I will raise a stop iteration error. Okay. And then after raising the stop iteration error, if it's not caught by like this for loop, right? We don't have any try catch statement, right? Which means that this whole thing will raise this whole function, the whole calling iter on this generator object will raise the stop iteration error that was raised by next of I. And since we know that if an iterator or generator raises a stop iteration, then it has stopped. And that is why this thing stops right here, if this goes to the end. Does that make sense to everyone? Why do we yield element? The reason why we yield element is because that's the point of this question is to iterate over the elements, right? So element is an element, so we have to yield the element. But it just depends on whether we've seen it or not, whether we actually do yield it. The basic stop iteration error equals false. Not necessarily. Stop iteration error is just like, I don't really know how to explain it too well because we haven't really gone over ever trying caching in this semester. But just think of it as the special flag that the function has seen. So like, you know, like when we call a function and if you did the recursion wrong, it will raise a recursion depth max error, right? Or if you do 1 divided by 0, the function will raise a division by 0 error. This is another error. Stop iteration is just like another error that is raised. And all errors that are raised, if it's not caught by a try catch statement, so it's a special kind of statement that you can process errors with. If it's not caught by it, then it will go to the very end and crash your program. But the thing is, iterators or generators are supposed to raise stop iteration errors at the end. So it will actually be specially caught. It will be, oh, I see a stop iteration error. Instead of crashing the program, I'm going to say that, great, the iterator or generator has finished. And that's why it raised the error.
I can answer Karina's question on text.
Okay. Can you explain why we're using L again? Because this generator function yields the unique elements of the iterable input. So we have to yield the elements of the input, but they must be unique. So we get the element, we check whether it's unique, and then we yield it if we haven't seen it before. Yeah. And also, I think this question is definitely doable with like recursion. You can probably do something along the lines of actually, it'll be hard to do it with recursion. Yeah, it'll be kind of hard to do with recursion because we can't use step, and we can't do. Yeah, it'll be hard to do with recursion. Anyway, yeah. You want to go on to the next question? We'll answer any other remaining questions about this part in chat. So, but right now we're going to the next question. Okay. Here.
Okay. So, what you have wished for, skeleton code. Your desires have been answered. So this is the next question called power generator, which I think the description of the problem is a little vague, so I'll try to be clear on what this does. So this is a generator that yields generator objects. So it's a generator function that yields generator objects. And each time you call next on this, this top level generator, it's going to yield a generator object that yields the powers of the powers of like an integer n, and that n increases for each time you call next on it. For example, if we look at the doc test here is like the key to understanding what this function actually does. So on the right-hand side, we can see that P1 equals the next generator. So actually, I may be able to actually draw on the screen. So P1, the base here, the base for P1 is 1, and the base for P2 is 2. And I'm drawing with my keyboard, my trackpad right now, so this is terrible. And the base for P3 is 3. And that will keep going forever. So each time you call next on this generator, it's going to yield generator objects that have a base of like 1, then 2, then 3. And the base is important because for each of these generator objects, generators generate things. So each of these generator objects is themselves going to yield all the powers of that base. So the powers of 1, we have 1 to the 1, which is 1 to the 0, which is 1. Then we have 1 to the 1, which is 1. Then we have 1 to the 2, which is 1, etc. Then 2, it starts by yielding 2 to the 0, which is 1. Then 2 to the 1, which is 2. Then 2 to the 2, which is 4. And likewise, we start with 3 to the 0 for this one. 3 to the 1. This is like so sad. I really need a iPad or something. Wait, it doesn't yield 2 to 0? Oh, sorry. Yeah, it doesn't start with the zeros. Oops. Just ignore all of those. I mistakenly thought it would start at 0 when clearly it doesn't. So ignore this column. I'm just going to keep drawing over it. Thank you very much, Sage, for catching my mistake. So it actually starts with the 1 power. So it starts with 1 to the 1, 2 to the 1, and 3 to the 1, and then moves on to the 2 power, then the 3 power. So 1 to the 3 is also 1. Okay. So this is reflected in, if you can see kind of what it's printing out, it's saying for each of these 3 generators, print kind of the first thing that they all have, then the second thing that they all have, then the third thing that they all have. So the first thing that they all have, we can check this first row here. It says 1, 2, 3. So that's what it prints out. It prints out 1, 2, 3. Then the second row here, it's like 1, 4, 9. So that's the second thing, kind of triple that is printing. So I feel like the printing is a little weird, but in essence, it's a generator. Each time you call next, it yields a new generator object, and that generator object will go through infinitely the powers of some base. So your job is to fill in the skeleton code. Are there any questions about the setup of the problem? We'll definitely give you some time to work on it. Then I'll give you a hint on how to, like, somewhere in the middle, and then we can go over the answer at the end. But are there any kind of initial questions on what the function is supposed to be doing? Okay, so then let's, I'll kind of wait here. We wait here for 5 minutes. If you have questions during the problem, feel free to ask. And then after 5, I'll poll for like a hint or something to see where we are. I need to stop attempting to draw. This is just probably making this presentation worse. I can erase.
How are you even drawing?
On the top, it says like view options, and then I click annotate.
Okay.
I mean, my laptop has a touch screen, so I could do like, but it's still like so bad. Like the touch drawing is just not ideal. One of those pens. Woo-woo indeed. Oh my God. Oh no, I just realized people were asking me private questions and I wasn't looking at them because I was on the other. No, I'm so sorry. Oh God. No, let me answer these. In the future, if you want to ask me a private question, ask other Dalton. that's the one I actually have all the question. That's the one I have the text pulled up on.
Or you can ask me.
Or you can ask Charles. Yeah, we're both fine. So every time it depends. Okay, so let's do a status check here. So go ahead and vote on your phones now. Click on participants and give me a guess if you want to have a hint, a hinty something to move forward, or no. I guess if you don't want one for any reason, which would be you're finished or you don't want a hint. I actually have no idea whether like I know the reactions go away after a while, but I'm not sure if the yes or no like is carried over from a previous poll. So I'm just gonna go and give you the hint now because I see a lot of yeses. So let's talk about what like how to approach, how to look at this section. So I think right like I see two sections of the problem. I see this part and I see this part, only because the top part is its own inner defined function. So we know that we must yield generator objects. So that's required. So our outer thing, how natural, we see a yield down here. So maybe, that means that pow natural, we're going to be yielding some generator objects. So maybe, oh, I can clear the yes or no of each question. Oh, maybe you have to do that, Charles.
Oh. I'll keep that in mind for future
yes.
stuff.
So so we're from, and this yield, let's try to yield a generator object in this blank down here. And for this function up here, because we're yielding generator objects, the only way to do that is to write a function that has some yields in it. So that means that this one up here, this inner one, these will be our inner nested generators, which are going to, do the 1 to the 1, 1 to the 2, then 1 to the 3, 2 to the 1, 2 to the 2, and 2 to 3 onwards, or 3. So it depends upon what the base is. There's a base and a power. Some other hints, we notice that this one up top, there is definitely no room for iteration up here. So this top one will have to be a recursively defined function that yields these powers. So you'll have to think about how to do that. It does use recursion. And the one on the bottom, we do see there seems to be some room for iteration. We have some sort of variable that might be changing over time, and we have a blank, which could be an if statement, but probably isn't. So we can throw some iteration in here to iteratively create generators, and then each generator will generate these powers. So hopefully that gets you a starting point if you didn't know where to start. And then I'll wait some more minutes, and then we can go over the solution. Okay, so whenever you think you have finished the problem or you just want to see the answer, feel free to check that yes button. And then when I reach some arbitrary threshold that I will decide in my mind, then I will go over the answer. We've not hit the threshold yet, so I'll wait like another minute. Alrighty, so if you're still working on the problem, keep working on it. You can mute me if you don't want to have any spoilers, but I think it would be pretty beneficial if we could get through one more problem before we close. So I would like to go over this now, the solution here. So just to display it on the screen. Oh no, I'm annotating. Here it is. Oh, okay. Here are the annotations. Thank you. So here is the solution to the power generator. So let me break it down for you. Maybe I can draw again. So let's start with the innermost part, actually, this innermost pow. So we know that this function, we want it to just kind of take some base n and yield all the powers of that base infinitely. So if, we're kind of given a base, so we're going to given a base like n equals 3, if n equals 3, then we're going to start with 3 to the 1, and then it's going to move up to 3 to the 2, and then 3 to the 3, infinitely long. So it's going to keep going forever. So we're going to use recursion to solve this one. And we can see at each step, we are going to yield the base to the current power. So if n is 3 and p is 1, it'll yield 3 to the 1. And if we're currently at the 3 to the 1 step, the next thing to yield is 3 to the 2, and then 3 to the 3, and then 3 to the 4, forever. So this recursive call here, how do we know the original value of p? We will get to that. If you sneak ahead to the bottom, we can see that we're going to start out with p with the 1 down on the bottom. But here we have this recursive call that will keep n the same. So the base is going to stay the same. That sounds good to us. And we are increasing p by 1. And recursively leap of faith style, this is saying we're going to yield from a generator which generates every single power of 3 starting at p plus 1. So if we're currently at 3 to the 1, that means we're going to now yield from a generator that's going to yield every power of 3 starting at 2, then 3, then 4, then 5. And that's exactly what we want. So this little mini generator here is going to yield all of the powers of base n, starting at some p. So how do we start out with this? Well, we know we want to start these out with 1 because all of our generators should start out with 1 as the exponent. So this outer part, this is generating our generators. So this is also infinite, but it's accomplished using iteration. So we have our classic infinite iteration while true. So this is going to go on forever. So while true, we are going to yield a new generator object. So we can see that we are actually calling this generator function, right? Pow's a generator function, but we're calling it, which means that we're going to be yielding a generator object, which is exactly what we were actually supposed to do given the problem. So this is perfectly right. And as Sage pointed out, thank you, that in the test cases, it did say that we wanted to, the test cases illuminated that 1 is the starting exponent. So we're going to kick off our powers with whatever n happens to be right now. It starts at 1 and keeps going up, and we're going to start out the power at 1. And then that will yield, infinite powers starting at n to the 1, and then n to the 2, and then n to the 3 forever. And we're going to keep yielding these, and n is going to increase each time. So our outer generator is increasing the bases, and our inner generators, each one going like horizontally, I guess, in the drawing, those were okay. Those are the exponents. So let's see. Would you say that most recursive generator problems follow this pattern, where you yield one thing and then yield from the recursive call? Probably most. Yeah, I could definitely agree. I would definitely agree with that statement because you need to have at least one real yield statement. If you only have a yield from, that's not good. Your recursive function will actually never yield anything. You need to have at least one like concrete yield statement that actually yields something if you're doing this recursive generator. So that's why we have this yield here. And then you probably also use a yield from because you want to yield from a recursive call. You might have some additional work in there, but these are definitely like kind of the two base parts of your recipe for creating recursive generator functions. Yeah. Okay. So can we do one last problem, the next one, Charles?
Yeah, sure. I think this part, we won't be as thorough with this one because we only have like 9 minutes left. But yeah, try working on this for like 5 minutes, then we just give the answer. But this is infinite list generator. So basically, you're given a list. Remember, this is actually a list, so you can index into it. And then essentially, this infinite generator takes this list and yields every element in this list. But when it gets to the end of the list, it cycles around to the beginning. So it kind of just yields all the elements. So for example, you have 1, 2, 3. You have 1, 2, 3. It does 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, continue forever. Things like that. Yeah, and it also did not modify the original list. So as we here, we've given you some skeleton code. We have the index starting at 0. We have a while statement. So how do we have to infinitely generate some stuff. And then we have the rest. So yeah, try working on this. I think for this question, we like the code is structured to do this iteratively, but definitely this question can be done recursively. It might be a good exercise to not to like after doing this part, not follow the skeleton and just try doing this whole function using recursion. That might be a good practice to do. All right. Okay. It's about like 5 minutes when it's at like 150, let's say 156 We'll go over the answer. All right. Okay. And as always, if you have any questions, just ask. Whoops. I don't need to do that.
I was muted. I was like trying to press buttons, but I was only controlling your screen. So then I accidentally like forwarded it, and you also did too. And then I realized I was muted, but I couldn't unmute myself because I was inputting keyboard commands to your computer.
Hmm.
So that was a big mess. Yes, thank you, Anthony. I am indeed face palming at this moment.
All right. So it's 1:56. I'll just try going with the answer right now. It's okay if you haven't finished. If you haven't, you can mute me. That's okay. So yeah. All right. So as with any infinite generator questions, we have the classic while true, because we want an infinite generator. So we can think about having while true. What are we doing in this? Well, we know that we have to somehow keep track of the current index that we are working with, because we have I is equal to 0. We also have to have some way of incrementing it, but also wrapping it back to the beginning. So here is the answer. So don't worry about this part. Only look at the left side. So we have while true. Essentially, we yield each element. So we yield the ith element. And then instead of just the usual I is equal to I plus 1 or I plus equals 1, we have to do I is equal to I plus 1, but then modulo by the length of list. So what this does is this thing will wrap back around. So if it's, say, the length of the list is 3, then when I will be 0, 1, 2. And then when I becomes 3, so if I plus 1 is 3, 3 modulo 3, well, that's 3 divided by 3 has remainder of 0. That means I is going to wrap back around to become 0. And then it's going to keep going forward like from there. So this is one way you can do to cycle to have a, what do you call it, an index just wrap back around infinitely by doing I is equal to I plus 1 modulo length of something. All right, and the yield part is pretty explanatory. We yield the element in the list that we need. Why do we not have to call iter on the list like the previous questions? So the previous question, we said that we're taking an iterable. And the definition of iterable is just anything that you can call iter on. Whereas here, we say it takes in a list. So we know that specifically is a list, which means that we can actually index into it. Whereas iterables, you don't necessarily, you can't necessarily index into a list. Could you also go with recursive case ways of solving this, please? Sure.
Yeah, I got another question on that as well.
Yeah. Actually, might as well just show it. Can you see my screen?
Yeah. Yes, we can.
All right. Okay. So here's IPython. Let me see if I can zoom in on this. References. Initial terminal size. Text appearance. Let me just turn that up. Sure. Okay, close. I don't know if that helped, but yeah, okay. So if you want to do this, you have def infinite generator. Okay. So I feel like the recursive way is pretty cool. So essentially, we first have to yield the first element, as we always do. And we have to somehow yield from this infinite generator, but have everything cycle around. So what we'll essentially do is this: yield, and then from infinite generator, okay? But the list we have to take in now has to start at the second element. So we have to do a list slice from the first element onwards to the end. And then we have to then get the first element and put that at the back. So the modulo 3, we can just do a list of 0 and put that at the end, like this. And this will be the recursive version. So yeah, so for example, I just wrote for example, for I in, what can we do? For I in range, let's do I is equal to 0, and then G is equal to infinite generator, and then let's just give it 1, 2, 3, 4. Okay, then if we do while I is less than, let's just say 10, then we want to just go, I don't know why I did a while loop, print next G, and then I plus equals 1. So this should print out 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, like that. So this will be the recursive version. It looks kind of elegant. It's a bit weirder because you have to do this part, this list slicing and concatenation, which is not very intuitive. All right. Also, it's 2. So thank you all for coming. We will stick around for a bit more to answer any more questions that you have, but you are free to go. I mean, you're free to go anytime, but yes, thank you for coming to this review session. We hope you enjoyed. Also, there should be other review sessions that are posted elsewhere as well, like on the playlist if you need to look at the previous ones. But yeah, we will stick around to answer more questions.
Thanks, everyone.
Yeah, thank you for coming. Yes. Okay. We go over the line.
Sorry. Could you quickly explain what copy index from 1 to the end plus copy of 0 does?
Yeah. Did we go over list slicing this this semester? I think so, right?
Yeah. List
Yeah.
slicing in scope.
In terms of why do you have to do like the list, like why do you have to add the list, like the first index of the list to the, like from 1 to the end? Because isn't that just technically giving you the list?
Yes, but the thing is we have this list, but everything is shifted over by 1.
Oh,
So if you don't have this part, copy is going to just keep decreasing until it's nothing, right? So we need to somehow of like keep track of the old one. So we essentially just kind of like shift it. We shift it and then have the back one wrap back around.
oh, I get it. Okay, thank you.
Yeah. Other questions? I think someone wanted me to explain the modulo part again. So essentially, whenever you, like modulo is an operation, so that it's like division, but it gets you the remainder. So the use of that is length of the list. Say if it's the length of the list is 4, then that means the indices of the list are 0, 1, 2, 3, right? So we want to constrain that this index 1 is always in between like 0, 1, 2, 3. So that means if we keep increasing it, it will become, it'll be 0, 1, 2, 3. And then when it gets to 4, we don't want that. So when it's 4, we know that 4 modulo the length of the list, which will be 4, would actually be 0. So we can see that when I gets to 4, it will actually wrap back around to become 0. And then for the previous ones, if you have 0 modulo by 4 is still 0, 1 modulo by 4 is still 1, 2 modulo by 4 is 2, 3 modulo by 4 is 3, and then but 4 modulo by 4 wrap backs around. So anything that's less than the modulo number, modulo by that number will just like be itself, it will not be changed. But anything after that will be like wrap back around and like, it will be cut until it's in between the range that you want. Yes. Any other questions that people have?
All right, I'm gonna end the recording here and see if I can get this uploaded.